Thank you very much, Zhigang, for the introduction and also for the invitation. I really enjoyed each and every talk that I attended. I have to confess, I didn't attend all because due to schedule conflict and meetings and so on. But I'm trying to attend as much as I can, as many talks as I can. And today, what I'm trying to talk about is really touch upon several things. So the title is Optimal Shrinkage Estimation in Heteroscedastic Hierarchical Models. So there's a few words here. First, I'm going to talk about shrinkage estimation. And in particular, we'll talk about how do we find the optimal shrinkage estimation. In the context is the heteroscedastic situation, meaning that unequal variance situation. We're going to look for the optimal shrinkage estimation in terms of risk property under the setting of unequal variance observations. So that's a basic background picture. And this is joint work with several collaborators, Larry Brown at UPenn, two former students, Xianchao Xie and Justin Yang. Right now, they're both on Wall Street, hedge fund. And so let's first talk about shrinkage estimation. And we're going to talk about optimal shrinkage estimation. Well, for statisticians, I think ever since graduate school, you should be fascinated or at least puzzled by shrinkage estimation one way or the other. And basically, if you want to trace all the way back, that dates back to 1950s. And Stein's a sequence of papers that sort of revolutionized the whole world of statistics. And basically, he introduced the idea of shrinkage. And in many cases, shrinkage can easily beat the naive MLE to a large extent. And the remarkable thing that this idea of shrinkage estimation not only revolutionized statistics, but also has wide-ranging applications in all sorts of domains. For example, if you talk about bioinformatics, chances are you already encounter some sort of shrinkage estimation. Many applications in bioinformatics use shrinkage estimation. And political science, for example, suppose you want to pull different election polls together. You want to pull them together to get a more informed estimate of who will win the next presidential election. And chances are there's also shrinkage used. And engineering, for example, image analysis. When you do image compression, automatically, in many sort of default softwares, let's say JPEG, shrinkage estimation is also part of it. So that's basically the impact of this this idea dates all the way back to the 1950s. And among all the shrinkage estimation, I guess perhaps the most famous one is the Jamestown estimator. So basically, the setup is actually remarkably simple, but the result is also remarkably shocking, at least back then when I was a student. And so the setting up is very straightforward. Suppose we have independent observations, xi. Each has its own unknown mean, theta I. Let's assume all the variants are equal A. In the classical paper, in the classical Jamestown, A is equal to 1. But now let's assume we know they're all equal. The variants are all equal to, which is A. And then how do you estimate theta? Well, the naive one is simply use MLE. But in this case, MLE simply use xi to estimate theta I. That's no-brainer, very straightforward. But this is Jamestown estimator, which is a shrinkage estimator. Instead of using xi to estimate theta I, let's shrink xi towards 0. And the shrinkage factor is given by this lambda hat over lambda hat plus A. Once again, A is assumed to be known. For example, A is equal to 1. And this is positive part Jamestown estimator. This is essentially the positive part Jamestown estimator. And the remarkable thing is that this one uniformly beats the MLE, no matter what the underlying theta is. Okay? And this, I have to confess that back then when I was a graduate student at Stanford University, the first time I encountered this, I was totally shocked. So first of all, and that's no difficulty. You can go through mathematical proofs to see that this one rigorously and uniformly dominates MLE. But it's shocking to me that how can someone come up with something like this? It's to me totally unnatural. And how can you even dream of such estimator, and let alone write down such a form? And I was back then, again, when I first encountered it, I was very puzzled. You can go through the mathematical proofs, but still, I feel like I don't have the intuition. Later on, finally, once I get it, finally, I think I got a rationale by reading a sequence of papers by Efron and Morris back in the 70s. They provide an empirical Bayes explanation, rationale for why this is a reasonable estimate, how you can come up with this estimate in the first place. At least by reading Efron and Morris' sequence of papers, I I'm at peace with myself in the sense that now I understand the rough motivation of it. So to motivate this type of shrinkage estimators, let's take the empirical Bayes perspective. That is, now let's pretend to be Bayesian. If you're Bayesian, you don't know theta i's. Naturally, you put a pri on the theta i's. To make a story simple, let's put a pri with mean 0 and unknown variance lambda. Okay? And this classical Bayes setting, or you can see this is a classical hierarchical model setting. And naturally, if you are Bayes, you are looking at the posterior distribution. The posterior distribution goes like this. The posterior distribution of theta I conditioning on the sequence of x1, x2, xn is given in this way. Normal distribution with lambda over lambda plus a, xi, this is mean, and this is variance, conditional variance, posterior distribution. And this actually gives us a way, give a nice rationale why this estimate can come out in the first place. At least for me, that's how I understand it. Maybe Stein has a totally different rationale to understand it, but at least for me, that's a way to understand it. And so that naturally gives the form of the shrinkage estimation, why this makes sense. And next, lambda is unknown constant. You don't know what is prime mean. So in the empirical setup, you use the marginal distribution of x to estimate lambda. So each xi marginally has normal 0, lambda plus a. So naturally, you use this estimate. Remember, lambda is variance. It has to be positive. So naturally, you end up with positive part shrinkage estimation. So that's at least give me a way to think about how to come up with a shrinkage estimation in the first place. And needless to say, over the past 70 years, a lot of intensive studies about the nice properties of Jamestown estimate and so on. And it is by far the most widely known one about shrinkage estimation. Now, this is the classical picture of shrinkage estimation. So basically, this is your original observation. And what you do, essentially, you shrink them toward the central location. In the previous picture, we'll talk about shrink toward 0. But you can easily imagine you can shrink toward the grand mean, x bar. And this is the picture of shrink toward the mean. So everybody get the same shrinkage, same amount of shrinkage, lambda over lambda plus a, applied to each observation, shrink to the central location. So that's a picture. Previously, they're widely far away from each other. But after shrinkage, they're getting closer together toward the mean and so on. Okay, that's a classical picture of shrinkage estimation. And this picture is taken from a 1977 paper of Efron and Morris. Now, the question we're interested in this case is a slightly more sort of applied question in one way, but slightly more theoretical in the other way. The question that insofar in the classical shrinkage estimation, and people typically assume A are the same, all the variants are the same. But in practical situations, very often you encounter situations, in applications, you encounter situations where the variants are not all equal. For example, if you do a political survey, in political science, you do survey, the survey chances of the survey quality are different. The sample size are different. Who conduct the survey, the agency, they have different reputation. So naturally, you encounter different variants. And in biological experiments, let's say in gene expression, and you do a study on a different gene expression level, chances are they're coming from, even in the same lab, chances are different people, different individuals do the experiments. And the experimental condition and the person's technical capabilities give rise to different variants. And similar things to, for example, survey on other cases, the sample size are different. Let's say different states have different size. If you do a survey according to state size, population size, naturally you have different AIs. So sample size are different. So naturally the question will be, now, just move slightly more practical. What if the AIs are not all equal? To make a story simple, let's assume at the moment that all the AIs are still known, but they're not equal. For example, one AI can be 1, the other AI can be 3, and so on. And in this case, how do you do the shrinkage estimation? Well, if the previous empirical Bayes method is any guidelines, so naturally we can try it again. Let's put a prior, similar thing. Let's put a prior on the unknown mean. And we can still calculate posterior distribution, rather straightforward. But in this case, the posterior distribution, if you look at the posterior mean, that's lambda divided by lambda plus AI. Previously, all the AIs are the same. Now they're different. And similarly, you can also talk about the marginal distribution. So this, if you follow the previous empirical Bayes derivation, naturally, this is the form of estimator you are looking after, you're going to use. But the interesting fact about this compare the two cases, same variance versus unequal variance, you notice that the shrinkage factor differs now. If you have an observation that has large variance, then you're going to shrink it more towards 0. Okay? Intuitively, for those observations has large uncertainty, you want to discount a little more. So you don't want to trust it that much as compared with observations that has a very small variance. Okay? And so here's the picture. Unlike a previous picture, everybody shrink to the same amount. And now people with observations with high variance will get higher shrinkage, where observations with smaller variance had a small shrinkage. And so in other words, if you compare this picture with the previous picture, you notice that in the previous picture, the orders are all preserved. x1, x2, x3. That also means that theta 1 hat is less than theta 2 hat, and so on. You get a sequence order. But in the heteroscedastic case, that unequal variance case, the order can be different. This actually has important consequences in scientific endeavors. For example, suppose you did, again, let's say biological experiment. You do a gene expression experiments, and you try to find which are the important genes for particular condition, what are second important genes for particular condition. And your previous sequence might be this number 1 gene, number 2 gene, number 3 gene. But the very fact that shrinkage estimator tells you that if the first experiment has a lot of variance, chances are after shrinkage, it's no longer the number 1 gene. Actually, in this case, that becomes number 4 gene. So that gives you the unequal variance case has a practical implication that it changes the order of the importance of the previous sequence. Okay? Now, let's look at the relative next question. And if you want to use this estimator, how do you this shrinkage estimator shrinking according to different variance? What is the hyperparameter lambda you should use? Well, here the interesting thing becomes interesting. And remember, previously your lambda hat, the positive Jamestown estimate lambda hat can be obtained from the empirical base perspective in the sense that we'll look at the marginal distribution of the x. Then we obtain lambda. Now, if you want to do the same thing, what essentially you have is xi you look at this marginal distribution, the variance lambda plus ai. Now, if you want to, now you have lots of different ways to estimate lambda. For example, you can use MLE to estimate the lambda. Then you get an empirical base MLE estimator. And you can use method moments, matching the second moment. And then you get an empirical base method moments to estimate lambda. And interestingly, in the previous case, in the previous equal variance case, the MLE, empirical base MLE and empirical base method moment, they're exactly the same. But now, in this case, they're different. When AI are different, and the consequence of these two estimators give you different estimate the lambda hat. Well, that's not the only choice. For example, we can generalize Jamestown in the sense that we know AI. What if we divide both sides by square root of AI? Then everything becomes equal variance, 1, 1, 1, 1, 1. We apply the same thing on the transformed data. And then once we apply Jamestown estimator on the transformed data, then we multiply everything back by the square root of AI. We get the result. And it turns out that's to give you a third estimator. And so these are now totally different. And in the previous case, in the previous equal variance case, these three are exactly identical. They're the Jamestown estimator. But now, even in this, once you have unequal variance, the three things are different from each other. Now the question is, which one should we use? That's a natural question. Or in general, which one is optimal? Is there any optimal one? If you want to use type estimator, is there any optimal choice of lambda? Now, at least we have three different distinct choices. In general, do we have optimal ones? Well, that's actually the question we're trying to investigate. And in the answer, the short answer is that indeed there is an optimal one, but that optimal one is none above. Okay, none of this is optimal. Okay, so what is optimal one? That's what I'm going to talk about. The optimal one is called sure, what we call the sure estimate. Sure stands for Stein's unbiased risk estimate. So this is a sure estimate. And so what is the sure estimate? Okay, so now let's first, we have to talk about the Stein's idea of unbiased risk estimate. So in general, let's see, we're evaluating the equality or the effectiveness of estimator. We have to talk about loss function. In the case, it's a natural loss function to use is a mean square error. So basically, we're looking at theta, the squared deviation between your estimator and the truth. And now, intuitively, we want to find the lambda that gives you the minimum risk. Okay, that is the minimum expected loss. Okay, and so we want to find the lambda that gives you the minimum risk. And with the idea behind the Shur estimate is that the risk, obviously, the risk is a function of the unknown theta, which is something you cannot obtain. However, we can find an unbiased estimate of this risk. We can find a statistic, meaning that we can find a statistic that can be calculated based on the data you have, and that statistic has a property that it is an unbiased estimate of the risk. In other words, this is a Shur statistic. For any fixed lambda, it is a function of lambda, but for any fixed lambda, if you calculate the expected value for the Shur, that is exactly equal to the risk function. So we can find this unbiased estimate. And why this unbiased is relatively straightforward, because you have a normal distribution, and this just involves second moment and so on. It's very straightforward for you to calculate and to verify this is the unbiased estimate. So here comes the natural idea. We want to find the lambda that gives you the minimal risk, and the risk is not something we can obtain because that involves unknown theta. And what if we try to find a proxy for this risk? In the sense that what if we're trying to find the minimizer of the Shur statistic? We use the minimizer of the Shur statistics as our estimate for lambda. And we want to minimize risk, which is not available. Let's try to minimize a proxy for it. So that's a Shur statistic. And so naturally, our estimate will be, we estimate lambda hat as a minimizer of the Shur statistic. Once we have the minimizer of Shur statistic, lambda hat, let's put it back into the shrinkage estimation. That will be our Shur estimate, the Shur estimate for the unknown parameter theta. Is that clear? So that's intuitively, that's a picture. Okay, so as I alluded to, this one is actually the optimal one. So naturally, let's try to talk about the properties. What are the properties? The first property is actually, if you remember, previously we mentioned that Shur statistics for each fixed lambda, it is an unbiased estimate for the risk function. And now, furthermore, we have this result. That is, uniformly, if you quantify the difference, if we measure the difference between the Shur statistic and the risk function, uniformly, that one goes to 0 as the sample size gets larger and larger. So in other words, you have, from a uniform perspective, the Shur statistic is uniformly close to the risk function. This is actually the indication why Shur statistics you would expect the Shur statistics, the Shur estimator have nice risk properties. Actually, this is not only it. In fact, we can instead of measuring the distance between the Shur statistic and the risk function, we can talk about the distance between the Shur statistic and the loss function. And this is actually much stronger than previous ones. So because in the loss function, we're talking about the realization by realization. Whether in the risk function, we already average out all the x. But here, we're not even average out the noise. Realization by realization, the Shur statistics is uniformly close to the loss function. And in the sense that if you look at the uniform division, that converts to 0 as p, the sample size, gets larger and larger. So that's basically tells us that, and minimizing Shur, as in asymptotic perspective, minimizing the Shur statistics is very close for minimizing even the loss function. So that's basically indication why you would expect strong risk properties for the Shur estimate. Okay, so here is now formal statement for the optimality. Okay, so here's the story. So suppose you use this type of shrinkage estimation. So now I'm using boldface, meaning that sort of R type of boldface. That means this is the whole vector. This vector multiplied by another vector. So A is the boldface A stands for A1, A2, A3 up to AP. So vector-wise multiplication. And so suppose you don't trust the Shur statistic, Shur estimator. You use any arbitrary estimate you can come up with. Okay. The story is that for any arbitrary estimator you can come up with, the chance that the Shur estimator is absolutely worse than your arbitrary estimator, that chance goes to 0 as sample size gets larger and larger. Secondly, if you look at the limiting risk, in the sense that sample size gets larger and larger, you can do no better than the Shur estimate. So that's basically the optimality result. So, so if you want to use this type of estimator, then the true estimator is the one you want to use from an asymptotic perspective. So that's basically the rigorous proof. Okay, and well, any theory needs regulatory conditions. So what are the regulatory conditions for the previous theorem? And essentially, that you only need these three regularity conditions, meaning that the AI square is bounded. You don't even have to AI square has a limit, has a mean or whatever, but just have to say it has bounded. It is bounded. Secondly, the AI theta I square is bounded, and so on. So these are essentially all the regularity conditions you need to guarantee this result, these two results. Okay. So now we talk about oracle property. What is oracle property? And so this is actually, Steve, the interesting question early on. Oracle, why you use the term oracle? Well, I use the word oracle, borrow the long tradition from Larry Brown and David Donahoe and so on. Okay, I use the word oracle property. And so here's oracle property. Let's see, suppose you have there's a higher being. The higher being not only, for any sequence observation, the higher being not only observes x, the higher being also knows what the true theta is. Okay, let's assume. And if for this higher being, if you want to use this shrinkage estimations, actually the higher being can tell you what is optimal lambda you want to use. Because the higher being can look at the loss function point-wise, realization by realization. For each realization, he can tell you, now this is the best lambda you should use. This best lambda, he has access to the truth as well as access to the observation. Okay, so this is the higher beings. So this important thing that this lambda tilde that differs from realization to realization. Because next time you have a different sequence of observations, this lambda tilde varies. Okay, because this lambda tilde is the one that minimizes the loss. And so this is lambda tilde is actually a function of x as well. It differs from variation from realization to realization. Secondly, and this gives the theoretical limit of how good an estimate can ever hope to achieve if you want to use this type of estimator. As long as you fix on this type of formulation, and then this is absolutely the best possible you can achieve. And here's an interesting theoretical result. And this theoretical limit is actually achieved by the true estimate in the limit. In the sense that if you use a true estimate and then you look at the absolute best you can do, the oracle estimator, and you look at the distance between the two, as p goes to infinity, the chance that the true estimate encounter a loss epsilon worse than the oracle estimator, that chance goes to 0. Secondly, if you look at the limiting risk is precisely 0 in the sense that, indeed, not only the true estimate is optimal, it actually achieves the best possible in the asymptotic limit that you can ever hope for to have. Okay, so that's basically the optimality about this true estimator. And the fundamental result, the fundamental reason why this is true is because the true estimate, the true statistic, is uniformly close to the actual loss. That's essentially the theoretical reason why it is true. Okay, so now so far we talk about shrinkage toward 0. The reason why we end up with shrink to 0 is because in the prior distributions we put a mean 0 for all the unknown quantity. Naturally, we can shrink toward the general location x bar. That can come from this formulation if we put a mu there. In the equivariance case, naturally your estimate for mu is x bar. But now, the interesting question would be, suppose I want to use this type of estimator. So previously, again, I'm shrinking to 0. But now, suppose I want to shrink toward a common location mu. What is this choice? What is a good choice of this mu? Well, at this moment, things also become interesting. In the equivariance case, a very natural choice for this mu is x bar. Okay? And want to shrink towards the central location. That way, the central location is simply the mean. But in the unequal variance case, which one you want to shrink to, that's actually a little bit unclear. Do you want to shrink to x bar? Well, maybe you don't, because the different observations have different weight, have a different variance. They can have a different precision. Why do you want to weigh them equally? Maybe you want to weigh them according inverse variance. And maybe not so. The reason is because if you look at the shrinkage factor already takes care of part of the unequal variance situation. So for the noisy observation, you shrink more. It's already been sort of part taken care of. So what is the best compromise of this mu? So at this moment, it's actually not very clear if you just look from this formulation. So a natural question to ask is that, now, in general, if we introduce a central shrinkage location, and can we determine lambda as well as the central location together from the data, rather than our just purely guess, whether x bar or weighted average or something? So that's a natural question next. Well, you can expect what we should do. We can use the show estimate again. So previously, we shrink to zero, but now let's have two unknown quantities, two hyperparameters, lambda and mu together. We look at the shrinkage. We look at the determination of not only the lambda but also the common shrinkage location together. And it turns out, if you do a little bit more math, and you can find a sure statistic that is unbiased for the risk function for any lambda and mu. So in other words, for any fixed lambda and mu, if you calculate the risk of using that previous shrinkage formulation, shrinkage estimator, and then you calculate the expectation of this sure statistic, it turns out for any fixed lambda and mu, the expected value of the sure statistic is precisely the risk function you're looking after. You're trying to minimize over. So now, follow previous ideas. We want to find lambda and mu that minimizes risk function. We don't have it because the risk function depends on the unknowns, theta and so on. But we have a proxy to it. What if we minimize lambda and mu according to this proxy? So that give rise to our sure estimator. And sure estimator, shrinking toward a data-driven location, mu. Okay, where the lambda and mu is joint minimizer of the statistic. Okay, so naturally, now we can talk about risk properties. And the risk properties pretty much carries over from the previous statement in the sense that, now let's look at the uniform deviation, the maximum deviation between the sure statistic and the risk function, and maximum over all the possible values lambda, maximum over all the maximum value of xi, and that uniformly, that deviation goes to 0 in L1. So now the very natural question probably you want to ask is, why do you want to constrain yourself to mu less than xi? Well, the intuition is very simple. So suppose this is a bucket of data. You don't want to shrink your data to the even beyond the extreme of x. You want to shrink your data somewhere in the data of the range of the data. You don't want to arbitrarily shrink your data to something far, far away from the bulk of the data, from actually the limit, the minimum and maximum of the data. So that's why you want to put this restriction around. Okay. And furthermore, we can strengthen this to loss function in the sense that if we look at the maximum deviation between the sure statistic and loss function, again, the loss function depends on each realization of x. So realization by realization, we can show that this maximum deviation goes to 0 in L1. Okay? So naturally, once you have these two results, now you can follow the previous line of logic. Now you can imagine, and essentially we can show that this form of shrinkage estimation with lambda and mu both determined from data has the optimal property, risk property, and which is indeed the case. So here's a story. Suppose you want to use this type of estimator, but you don't want to use the sure estimator. You use your arbitrary way to figure out lambda, your arbitrary way to figure out what the mu is, and the property is that the loss that you encountered by using sure statistic, that is epsilon worse than this arbitrary estimator. That probability goes to 0. Secondly, if you look at the limit, in the limit, as sample size gets larger and larger, you can do no better than the sure statistic, than the sure estimator in terms of its risk property. Okay, and similarly, you can talk about oracle properties. And the oracle property carries over. Now the oracle is that suppose we have higher being. The higher being not only determines what is optimal lambda, but also determines what is optimal mu, realization by realization. So in other words, the higher being look at your data and also look at the truth, and then find the best lambda tilde and mu tilde that matches these two, realization by realization. And this is give you a theoretical limit of the lower bound that whichever estimate of this form can ever hope to have. And it turns out the Shur statistic, the Shur estimate achieves this lower bound in the sense that the chance is that the loss function, the loss that you encountered is epsilon worse than the oracle one, and that is chance goes to 0. Second, in the limit, the risk of the Shur statistic precisely is equal to the limit given by the oracle estimator. So from these two properties, essentially tells you that as long as asymptotic is concerned, and you can do no better than the Shur estimator. So that's why it is optimal one. Okay, and that's, well, if you think about our development so far, essentially we are looking at estimate of this form. And if you look at all the risk properties, actually it doesn't involve the shrinkage estimation. It doesn't involve the Bayesian formulation at all. And why we end up with, but the motivation for us to have this type of estimator, that does come from the Bayesian perspective. So under the Bayesian you put on the Bayesian setup, that gives you a specific parametric form, and then you want to optimize over lambda and so on. So now the natural question would be, instead of looking at this one, is this the best we can do? Well, the reason we ask this is because although we have optimality, but that's optimality over this type of estimators that has this fixed parametric form. The question is, can we do better? Can we move beyond this type of estimators? Well, so once we ask this question, we move beyond the classical empirical Bayes setup, because this one is motivated from empirical Bayes. Now I want to go beyond empirical Bayes. Well, the answer is that actually we can do better than this one if we are willing to move on to a larger class of estimators. So here's the motivation of this larger class estimator. It is still a shrinkage estimation, but formulated a different way. It is still shrink toward the central location mu, but it no longer requires you to have this parametric shrinkage formulation. It's taken away. Rather, we still have a shrinkage estimation, but rather the requirement is that we have a monotonic requirement. That is, for noisy observations, we shrink more. For more precise observation, we shrink less. As long as we require this monotonic relationship, we move beyond these parametric forms. So now we realize that this parametric form is just a special case of this, in the sense that we give BI a particular formula. Now we even move that one away. So for BI, we only require to be monotonic in terms of the variance. Now this is a much bigger class of estimators. Okay, and now we're asking this question. And from this class of estimators, can we determine the optimal one? So in this sequence of, in this question, we not only have to determine the mu, the central location, but we also have to determine each and every B, B1, B2, B3, as long as the B1, B2, B3, they are monotonic according to the variance. Okay? And naturally, once we talk about this estimator, this is no longer a parametric estimator. It's actually non-parametric, semiparametric, in the sense that we still shrink toward the central location, but we no longer impose any parametric restrictions on the form of B. Okay? And so, well, again, once we talk about this, naturally the question would be, what is the optimal choice of the sequence of B as well as mu? Well, if the previous result is an indication, probably the first thing we want to try now is let's try the Shur again. Okay? And it turns out, and for any fixed sequence of B1, B2, B3, and mu, and you can always, we can still find a unbiased estimate for the risk function for the sequence of B1, B2, BP, and mu, and that is given by this formula. Again, the verification is very straightforward. You take the expectation of those sides, and then a few lines, you realize the expectation of this is exactly the same thing as the risk function. Therefore, once we have this result, once we have this sure statistic, natural thing that we want to minimize the risk. What if we try to find the sequence of B and mu that minimize the sure statistic according subject to the criterion that the B's are monotonic. And then we find, once we minimize this subject to the criterion monotonicity, and then we'll put it back to the estimator. That gives us a sure estimator. Okay? And if the previous result is an indication, it turns out we have similar stories here. The similar story is that the sure statistics is uniformly close to the risk function, and also it is uniformly close to the loss function, and uniform over all the monotonic sequence, uniform over all the sequence that B1 less than B2 and so on. Okay. And similar, we have the optimality result. Suppose you want to find your own sequence of B, as long as they're monotone, and you can show that the chance that you encounter loss absolute worse than this arbitrary sequence, that chance goes to 0. And secondly, in the limit, the sure statistic achieve the best possible risk that you can ever hope for. In a sense, it's always smaller than or equal to the risk for any arbitrary estimate you might come up with. Okay. Fundamentally, these results come from this uniform closeness between the loss function and the sure statistic. Okay. So far I'm talking about classical normal settings. Normal mean theta I is unknown, and AI assumed to be known, and so on. So now let's go beyond this. It turns out this structure, this idea of using sure statistic find the optimal values for lambda and mu, and later on for B and mu, can be extended over to more complex, more general settings, and it's not unique to normal distribution. And as a matter of fact, let's talk about larger class of distributions. And let's talk about quadratic variance function, distributions with quadratic variance function. So what is this type of distribution? So basically, suppose yi has mean theta I, and the quadratic variance function meaning that the variance of yi is quadratic in terms of theta I, where tau I is the sample size. So you can imagine yi is average, within group average, where the group sample size is tau I. Okay? And then we have this if distribution on y satisfies this quadratic function, and this y is said to be, this yi is said to follow a distribution with quadratic variance. So what are the examples of these distributions? Lots of exponential families falls into this. Normal distribution is actually a very special case. In the sense, nu1, nu2, these two constants are both 0. And that's normal distribution. Poisson distribution, mu1 and v2 are 0. Nu0 and v2 are 0. v1 is equal to 1. That's Poisson distribution. And same thing, binomial, you have these two. Okay, binomial is p1 minus p. So you don't have this. You have this and this. And so on. And gamma distribution, negative binomial. So essentially, a lot of distribution from the exponential family follows into this formulation, and including gamma distribution including exponential distribution as a special case. Not only so, but the classical location scale family falls into this. For example, T distribution follows this. In the location scale family, these two things are both dropped out, and so you get a special case of quadratic variance function. So in other words, when you talk about quadratic variance function, and you can talk about exponential families as well as location scale family. And so in this case, we want a simultaneous inference. We want to have a simultaneous inference of theta I. That is a group mean. And now let's assume within group sample size, lambda I, tau I is observed. It's known. For example, if you do a survey sampling, for this particular survey, you surveyed 500 people. For this particular survey, you surveyed 2,000 people, and so on. So let's assume tau I are known. And we want to get a simultaneous inference of theta I. Okay, and now motivated by the previous discussion under the normal setup, naturally we can talk about semiparametric shrinkage estimations. We want to shrink the estimators toward a central location mu, and where the shrinkage amount is monotonic in terms of the sample size. The larger the sample size, the larger the number of groups, and the larger the group, the smaller you want to shrink you want to perturb it. And the smaller the sample size, the noisy the observations, the more you want to shrink toward it. The more you want to shrink it. So this is clearly, now you can see that this is motivated by the previous normal setup. In the case tau I, we know the group sample size. So let's try to make a monotonic on the groups, on the group sample size. Okay, well, to do that, now you ought to define natural question, what is optimal one subject to the monotonic requirement? And what is the optimal choice, B and mu? Well, if the previous any indication, you can still do the same thing. But now we no longer call it sure, because sure Stein's unbiased estimate, that works only for the exponential family. Now we'll also talk about location scale family. But interestingly, we can still find an unbiased risk estimate, but it's no longer the Stein's exponential family formulation. You can still find an unbiased risk estimator. So this formulation covers the exponential families as well as the location scale family. Now, once you have the unbiased risk estimator, you can do the same thing. Now, at least procedure-wise, you want to find the monotonic sequence, B1, B2, B3, and that minimizes this risk estimate, the unbiased risk estimate, and subject to monotonic requirement. And then once you figure out the sequence, you put it back in the equation. That's what you can have. Okay, optimality. So now optimality. You notice that regularity condition A to E, previously A to C. Now, because you are talking about more general classes, there's the two additional conditions which are relatively mild. And under this regularity condition, under the set of regularity conditions, you can still have the same optimality result in the sense that suppose you don't use this this URE estimate, unbiased risk estimate estimator, and you want to use something else, and then chances are your absolute worse than the arbitrary choice, that chance goes to 0. Secondly, if in the limit, you also always encounter a larger, or at least as big as the risk of the sure estimate, of the URE estimate that you encounter. So the result essentially parallels previous ones. But I have to say that the proof each time we have a new proof, the proof gets a little bit harder, because previously, only in the beginning, you don't have mu, now you add a mu, now you add another thing, so you add another distribution, whole distribution family. So each proof is a little bit more involved. You move off the ladder, but once you have previous indication, and you can expect this result will hold. Okay, now we can also talk about parametrics. So if we talk here, it's pretty much semi-parametric. You can also imagine we can talk about parametric formulations and so on, especially in the exponential family. In the exponential family case, you can talk about conjugate price and so on. You can derive the same parallel sequence of observations, parallel sequence of result. But in general, based on our empirical observations, based on our theoretical result as well as empirical observations, in general, the semi-parametric ones works better than the parametric ones. The precise reason is that the parametric ones give you a too restricted form for the specific formulation, for specific estimate you want to use, while the semi-parametric ones moves away the parametric form as long as it's monotonic. So naturally, you're talking about larger class estimators. You optimize over a larger class estimator, chances that you're getting something better than the more restricted ones, and which is indeed the case. Later on, we'll show you some numerical examples that indeed the semi-parametric ones, the larger class works better than the restricted class. Okay, so now that's not it. Let's move beyond. And in many statistical questions, and in addition to x, in addition to the y you want to estimate theta, you also have a sequence of predictors, linear predictors, x. You want to do a linear regression, chances are. You want a quadratic regression, and so on. Now let's try to extend the whole structure to linear models. Okay, so in the linear models, the typical setup for linear models like this, right? Yi still has the mean theta I, Ai are distinct from each other, but theta I now, in order to add a good estimate of theta I, we also notice that we have a sequence of predictors, a sequence of observations, x1, x2, xp. So now I'm arranging the covariance in terms of column vectors rather than row vectors. Probably in classical literature or something, maybe you tend to like to use the row vectors, but I want to emphasize now I'm talking about column vectors. For each observation, I have a column associated. I have a column x1 associated y1, column x2 associated y2, and so on. Okay, but it turns out once you want to formulate a shrinkage estimation, in the linear regression case, in the linear model case, actually there are two different ways you can think about how to formulate a shrinkage estimation, how to formulate a estimator, a Bayesian estimating actually. And the first way to formulate this is to assume theta I, the unknown mean, that regression mean, the regression function, or the mean, and a mean of yi, that is normal. The mean is linear in x with variance lambda. That's one way you can formulate it, in the sense that theta I itself is xi beta plus some noise. Okay? The second way is actually the more classical Bayesian way to formulate it. Beta, if you think about linear regression, beta is unknown, and then you put pi on beta. So that gives rise to the ridge regression and so on. And so that's a Bayesian formulation. The Bayesian, you put theta absolutely equal to x transform beta, and you put a pi on beta. So these are two different formulations. Think about it carefully. In the second formulation, theta always lies on the linear regression line, while in the first formulation, theta jitters around the regression line. Okay? So these are the two formulations. And the first theta is sort of jittered away from the linear combination, whereas here, beta, you first draw beta, and then you multiply by x. That is your theta, and then you generate the yi. So these are two different formulations again. Two different simple formulations. Once you want to talk about predictors, the present of predictors. Both are actually valid models, and depend on which one you're comfortable with. But both are very natural extensions of the Bayesian, of the classical univariate estimation. Okay, so now let's talk about linear models. Now we have two different models. One I call it a hierarchical linear model. The other we call Bayesian linear regression. Bayesian linear regression, you directly put the price on regression coefficient, where here you put the price on the mean. Okay, and so it turns out under this Bayesian formulation, and the posterior mean of y has different formulations. The posterior mean of y on the first model, which is this model, and that has a more familiar shrinkage estimation in the sense you shrink theta hat toward a linear combination of x. So now the mu lives in the row space of x, because you are talking about linear predictors. So previously, if you remember, if you compare this formulation with the formulation we talked about early on, previously, because you have no regressor, you have no predictors, mu can be anything. But now you require your mu lives in the row space of x. Okay, so you shrink toward a central location, where the central location is restricted on the row space. Well, in the Bayesian linear regression, remember you put the prior directly on beta, so essentially you get something similar to the ridge regression, and you get a formulation. You got a little bit more complicated formulation, and you get x transpose beta, this is essentially the posterior mean of the beta, and which is the weighted average of your prior and your weighted least square. So this is essentially the formulation you obtain. And in the ridge regression case, your beta 0 is 0. You get this formulation. That's precisely ridge regression. Okay? So you got two different ways to generate this. And similarly, this is parametric formulation. Parametric formulation, essentially, we still assume this precise parametric models on the prior and so on. We get a parametric formulation. That's why we get the lambda, the fixed lambda, we get this particular form. And motivated by the previous case, we can also talk about semi-parametric models. But we have to talk about semi-parametric model under two different models, under two different formulations of the linear regression model. The first formulation is relatively straightforward. So we shrink toward the row space of x, and subject the monotonic requirement. This is the most straightforward, very straightforward interpretation of this. So in particular, BI, the parametric form for BI is this formula, but now we move beyond the parametric form. We only require BI to be monotonic in terms of variance. The larger the variance, the stronger the shrinkage, and so on. So this, model 1 is relatively straightforward to formulate, and model 2 is a little bit more involved to formulate, but we can still do it anyway. So model 2, remember, the model 2 will directly work on the regression coefficient. we directly work on the regression coefficient. That's the result. And we essentially get a generalization of the ridge regression. And now, in order to see how this generalized to in a parametric sense, we have to do some sort of spectral decomposition. We look at eigenvalues. So in other words, the previous variance and previous ones that control the shrinkage factor now become the eigenvalues that controls shrinkage factor. So in the sense that, okay, mathematics are a little bit long, but you can still do, essentially you want, now because we're looking for the regression coefficient space, and we do some rotations and do some stretchings. Essentially, we can rewrite this estimator in terms of this formula. It's a little bit long, but the important thing is that if you do some spectral decomposition, essentially what you find is that you're under the parametric structure, what you encounter is a shrinkage here. This is essentially lambda over lambda plus dk, lambda over lambda plus dk, and this is dk over lambda plus dk. So these are the essentially shrinkage factor we're talking about, where the d1, d2, d3 are the eigenvalues of this matrix. So you do a spectral decomposition, you get eigenvalues and so on, and you'll find that the shrinkage is monotonic in terms of eigenvalues. So that replaces the previous variance and so on. And now, once you have this, rewrite this whole formulation under this scheme, and now you can talk about semiparametric shrinkage as well. Now the semiparametric shrinkage become you require your shrinkage amount is monotonic in terms of eigenvalues of this matrix. That's essentially carries over. So the mathematics is a little bit more involved, but the same thing happens in the sense that, again, since they are working on the regression coefficient space, you rotate the space a little bit. You look at the spectral decomposition, and then you require your shrinkage is monotonic in terms of eigenvalues. Largest, second, and third largest, and so on. So you generalize things over, except the formula is a bit lengthy, but the same intuition carries over. You just replace the variance by the eigenvalues. Okay, and then now, once you have this, once we move on to talk about the semiparametric structure, semiparametric estimators like this for model 1, and semiparametric like this for model 2, you can talk about, now we can still talk about the same thing. And we can talk about what are the optimal ones. Well, the optimal ones, if all the previous slides is an indication, let's look for the unbiased risk estimators. In the sense that for any sequence of B, and for any fixed shrinkage location mu that lives within the row space, we can still do the same thing. We can find the unbiased estimator, and then we find unbiased estimate of risk. Once that means that what if we minimize the sequence of B and the mu in terms of this URE statistic, and then we put it back in the equation, and that gives another estimator. So that, if you follow previous slides, this is the natural extension here. You can do the same thing for the model 2. In model 2, essentially same thing, except in model 2, you work on the regression coefficient space, and you do some rotations and so on. But the same story carries over, essentially. And you can find the same, you can find, in Spirit, you find the same type of estimators by minimizing the URE statistic. And similarly, you have the optimality result. And essentially, if you come up with any arbitrary estimators, as long as that arbitrary estimator has the monotonic relationship there, we can show that the URE estimate that we come up with by minimizing that URE statistic, that one is essentially optimal. In terms of limiting risk, it's always smaller than equal to the arbitrary one you come up with. And in terms of loss, the probability is the absolute worst. That probability goes to 0. And same thing for model 1 and model 2. Okay, and so far things are a little bit abstract, and especially everything now. We talk about asymptotic result. What does this type of estimated work in practice? And so now let's look at the concrete examples and as an illustration. And this by now is also a classical example, a neoclassical example. That example collected in Larry Brown's example. This data set is based on Larry Brown's 2008 paper in Annals of Applied Statistics. That's basically baseball players. And the story is rather simple. And let's go back to one particular season of Major League Baseball, American pastime, Major League Baseball. And let's break the whole season into two halves, the first half and second half. Well, in Major League Baseball, there's a sort of all-star play sandwiched between the two halves. So it's very natural to look at all the data that before the first half, that is before the All-Star game, and then the season after the All-Star game. So natural, let's break it into parts. And so for the first season, so now we're looking at the particular season of baseball play, and 2005-2006 season. Let's break it into two parts, and the first season, second season. The goal is that suppose we only have the data from first season. For each of the players, we have this performance for first season. Let's try to predict, I'm sorry?
What's being measured? What's the aspect?
Batting average. Batting average. Precisely the batting average. Okay, I didn't, batting average. So for each of the players, you have the number of at-bats, namely that how many times this guy has tried to hit the ball, and what success this guy hit the ball, and so on. So you got a success rate. You got the statistics, how many trials, how many success, and you have the result. You have observation for the first half season. You want to predict the performance of this guy for the second half season. So that's a prediction result. For the first half season, we have 567 Major League Baseball players. We have all their statistics, and we want to predict the outcome for second season. Okay. So in this case, if you think about it, what is a model for describe this? A very natural model is binomial. So this guy has total number of trials in Nij for the player J as season I. So I is 1 or 2, first half or second half. J is the individual player. It's very natural to think about this guy has, we're talking about binomial distributions. This guy, his ability to hit the ball is Pj, and he has Nij trials. For the first season, he has N1J trial. For second half is N2J trials. And we're trying to predict the PJ. Okay? We'll look at the first season and predict the second season. Okay? And we're dealing with the binomial distributions. So a very natural way to deal with binomial distributions is to transform it into roughly a normal distribution. The classical transformation for binomial is arcsine transformation. So you arcsine square root, you transform every binomial into binomial essentially into normal. Well, that's a slight twist. We add a 1/4, 1/2, and that's basically to stabilize the transformation a little bit more. But roughly, that's arcsine transformation. After you're doing the arcsine transformation, essentially you're reducing everything into the normal setup. And the unknown mean theta j. Theta j is related to the binomial probability in this arcsine formulation. And then now the variance are known. The variance is basically sample size. How many times this guy is at bats? Okay? So that's a whole picture. We're trying to estimate theta j. And then we're going to use the second season to validate our estimate for the theta j. We estimate theta j, we transform it back, we get a pj. So we're going to use the second season to validate our predictions, our estimate for pj. Is that clear? So that's basically set up. So in other words, we have estimation, first half, we estimate the second, we have validation for the second half. So for the second half, in terms of validation, we have 499 players. Because some players, for the first half season, they got dropped. They are behaving too badly. They got demoted to the minor leagues. Or they got the injuries. They take out the sequences. We don't have data for this. But roughly for 500 up players, we have that second season data. So we can do the validation. Okay, here's a lot of rows, but let's first talk about columns. First, we put all the baseball players together. But actually, American baseball is something interesting. And there are pitchers and non-pitchers. Pitchers are the guys professionally trained to throw the ball. And batters are the guys who professionally trained to bat the ball. And essentially, there are two different species. One is trained to throw ball all the time. The other is trained to hit the ball all the time. But interestingly, there's some minor details. The Major League Baseball is divided into two divisions. One is called American League. The other called the National League. The interesting thing is that in National League, people require the pitchers also to bat the ball. Where the American League doesn't require that. So anyway, that's some peculiar. I never figured out why do you want to get a ball who professionally trained to throw the ball to bat the ball. It's like in the soccer, you ask the goalkeepers to be the striker. Why do you want to do that? I don't understand. But anyway, you get this data. You got a pitcher and non-pitcher. So pitcher, anyway, has to bat the ball anyway, and the non-pitcher, obviously, they are the batters. They have to bat the ball. So we have, if we put all players together, and then we have look at them separate groups. Okay, and so also we have the covariate, whether we want to use the covariate or not. What is the covariate here? Actually, a good covariate is the total number of trials this guy have. The point is that if this guy is good, chances are the coaches or the general managers will put this guy more frequently. So this number of sample size is actually roughly related, positively related to the performance. If this guy is good, the chance of this guy is there for a whole season. If this guy is very bad, maybe only twice this guy gonna try. Okay, so the covariate is actually, the sample size itself is a very important covariate. So now let's look at, we have using sample size, using the covariate or not using the covariate. Okay, now, there's a lot of rows here, but roughly the rows can be grouped in this way. First, ordinary least squares, or weighted least squares. In the case you have a predictor, it's understand ordinary least squares, weighted least squares. In the case you don't have a predictor, you just throw in 1, 1, 1, 1, 1 everywhere. That's still your ordinary least squares. And then we have the parametric empirical Bayes. Parametric empirical Bayes, method moments, and MLE. As I mentioned, because variance are different, sample size are different, these two things are different estimators. Then we have the Jamestown estimators. And the Jamestown estimators transform into the regression setups. And then we have the parametric URE estimator. Remember, earlier I mentioned in this set of optimal estimators, we can talk about parametric formulation as well as a semi-parametric formulation. So now we'll compare 1, 2, 3, 4, 5 groups of estimates together. Okay, and then we'll also compare with covariate and without covariate. The first question, and before we do that, the first question, let's look at the columns. And also a naive estimator. What is naive estimator? Naive estimate is no-brainer, not doing any calculation. Simply use the first half average as the predictor for the second half average. Don't do any shrinkage. Okay, simply PJ hat from the first half. That's the estimate for the second half. That's a naive estimator. And we took naive as one. In other words, when we look at the numbers, we always divide it by the number of naive. So that we get a contrast. We don't lose the rough picture, the general picture. And the first question is that, now let's look at overall performance. If we don't distinguish, if you don't put the pitchers and you don't separate the pitchers and non-pitchers, the general result is that if you don't separate them, you notice that if you use least squares and so on, that's not much better than naive. Sometimes even worse than naive. However, once you separate the pitchers and non-pitchers, you notice that general, the result is so much better from pitchers, from the naive estimate. This is actually very intuitive. Intuitive in the sense that you have two different species. You shouldn't try to shrink them together. They're two different universes. You should consider them separately. That's the general message. Secondly, let's look at with covariate and without covariate. In general, if you compare the columns, the highlighted columns versus non-highlighted columns, you'll notice that with covariate, general tends to be much better, better than without covariate. Once again, the reason is that the number of players, the number of trials this player gets, that's actually a very good indication of this player's capability. A good player tend to try a lot. So that actually has a lot of information about his performance. So using a good covariate gives you significant leverage in terms of doing the prediction. Okay, the next one is that if you focus each column, if you focus on each column, try to look for the best numbers. Okay, you find that generally the best numbers are clustered around the semi-parametric ones. For example, 0.4 versus something 0.5 to 0.8. And the same thing happens if you look at the pitcher group, that's 0.07, and everybody else is 0.1, 1 and above, and so on. So in general, another message is that in general, if you want to look at the best performing result, best performing method, that tend to be the semi-parametric class. That essentially indeed tells us that not only we have some theoretical results, but for those real applications, we see the evidence of indeed we have some superior performance in comparing with other methods. And another interesting question will be, in this case, the sample size is close to 500. And so that indicates as one sample that reaches close to 500, the asymptotic starts to kick in. Actually, you can do a simulation study. Due to time constraint, I will not show the simulation study. The simulation study shows that, in general, for p as large as 100 and so on, and the asymptotic already start to kick in. You see the performance difference. Okay, so finally, let me conclude the talk. So we conclude shrinkage estimation on the setting of normal setting and non-normal setting, linear, as well as linear regression. We talk about unequal variance setup. And we propose this unbiased risk estimate as this family of unbiased risk estimators. And we can talk about both semiparametric ones and parametric ones. And we enjoy some good risk properties. We enjoy the hierarchical property and enjoy the risk optimality. And numerical performance seems to be quite competitive based on this concrete example. Acknowledgement of these are the collaborators and former students and collaborator Larry Brown, and the fundings from NSF and NIH. Thank you. And here are the references for the three papers that my talk based upon. Thank you very much. Hi.
So you're saying you do better on predicting the pitches than performance?
No, well, yes. We're measuring the performance on your predictor for the second half. For the second half, you measure it. And you calculate p hat, and you measure the second half p versus your predicted p. That's a measure of difference. You measure it for not only the features, but also the non-features.
Yeah, but I was thinking that maybe you're able to predict the pitches better because their band performance is so poor.
Because that's exactly you see it. Actually, you see it. And the features, you see the numbers are generally smaller than non-features. That is basically the features. They're pretty poor. You can predict them relatively accurately because they're pretty bad. And where the non-features, they have the whole spectrum, and it's more difficult to predict. You see this from numbers. If you compare general this group versus this group, you see the difference. And it also tells us that it's a bad idea to put them together, shrinkage them together, because they're two different species. If you shrink them together, you destroy each and every in certain sense. Yes. Let's talk about relative performance. Relative performance to the naive. So how much improve upon the naive? I'm not showing the exact result for naive. So for the exact numbers actually might be different, but we're not talking about how much improve upon the naive estimator. Yes.
And you take the minimizer of the Steins and bias risk estimate. If you look at those two as random variables, surprisingly, they tend to be negatively correlated. Has anybody found such a thing in this world?
We found something similar to that, but we didn't substantially large enough to make a formal claim about it. But if you look at the overall difference between the Stein and the risk, they're very close. And the lambda might be quite some distance apart, but the overall functional difference is relatively small.
I was going to say it's kind of an interesting place where it's worth doing the mathematics, because you wouldn't expect that because of the way the curves are. You'd expect them to be correlated positively.
Yeah. So precisely this, early on, why we venture into this? Early on, when we try to shrink toward the general location, I said, in the beginning we said, why don't shrink to X bar? But then the more you think about it, it's not a very obvious way to shrink towards, because the shrinkage factor already takes part of the weights, take part of the different, account for the variance difference. How do you find the balance between two? Only through the math we find it. Yes, Anthony.
I've never quite understood in this context why one doesn't use the binomial results.
We use the binomial result.
But these here are based on this arc sign.
Yes, based on the arc sign, we have the binomial.
Results. Why don't you just use those?
Because we don't have the regression. We want to do the regression. Otherwise, it becomes generalized linear regression. We haven't had established form theory for the generalized linear regression. We essentially talk about We essentially talk about some sort of like logistic regression or something, because you want to do the regression. That's why we want to have a fair comparison between with regressors and without regressors. We don't have the general theory for general linear models yet, so we have to do it everything on the normal scale.
So generally, you have all this AI as known, so the variance.
Yes.
So if it's unknown. So that's what I mean. Generally, what's the shrinkage for this covariance structure?
We didn't have a covariance structure here. What you decide is a subtle thing, right? It could be in the Major League Baseball players, might be some covariance correlations. Now we're assuming they're independent of each other. You might see people from the same team, they might correlate with each other. We didn't take care of that. That involves another layer of modeling. You might have a block structure, like people from the same team, they might get by the same coach or by the same manager, they might get by the same crowd and so on. We didn't take care of that. We just assume they're independent, apply what thought we have.
Can I go to your last slide? The one with the references. The last. The final one. Yeah, this one. So you talked about, I didn't know every work area. So there, so afterwards, because I think initially there is 2008 paper, right? We talked about baseball and that was, if I remember correctly, he did his upside transformation.
Yes.
But did he also talk about the non-parametric empirical base?
He talked about non-parametric empirical base. Actually, the table is too small. There's another 5 rows or something on a non-parametric empirical base, and also has a non-parametric density sort of based on estimators here.
So can you go back to the last slide? Yeah. Because that's my ignorance. And so there, I mean, essentially these Gaussian arrows paper, you and he sort of go together.
Yes.
You basically use the short estimate.
Yes.
Okay,
Yes.
And also, but there was no URV yet.
That's URE is in the second paper. URE is in the second paper because this paper also covers location scale family. Once you move on to location scale family, there's no Stein's unbiased risk. Stein's moved away from it, but you can still formulate the idea. Try to find unbiased risk estimator. But that's not the Stein fashion.
So
Exponential family, you can still have.
monotonicity.
You still have the monotonicity.
So that's in that paper.
That's in this paper, second paper.
Oh, okay.
So the first paper only talked about normal case. The normal case setup. This one generalized to exponential family as well as the location scale family. This one talked about linear regression case.
Oh, okay.
So that's
and then this the last one, you sort of distinguish between the two regression models, am I right?
Yes.
One is the hierarchical.
Yes.
And the other is the
Bayesian, yes.
Prime,
That's right. Yes. This one covers both regression generalizations. And they're from our website.
Oh,
They're all available from website. You click on it, you got a PDF file.
Have you put some plots of your predicted values versus your observed? Have you taken a look at the distribution of those?
A distribution on what?
Your predicted values and your observed values?
You mean the deviations?
Yeah, the whole distribution.
Yeah, we have this picture. Well, that you can do this through simulation. You get, in general, as sample size gets larger and larger, you plot.
I mean for the baseball data. I mean this is for the baseball data.
For baseball data, I don't have a plot here.
Do the results look much different depending on the method? So do the predictions really look much different?
This is the result, right? The prediction looks sometimes 5 times difference.
Yeah, but it's not looking at the distribution of values. So your distribution of predictions.
Distribution on what? Each player is different. So you look at the
players.
you.
So I guess what she means is probably the box plot of your this prediction.
Oh, well, I didn't have that plot. No, I didn't have thought about the plot. We didn't have that plot. But in the paper, you can also see the shrinkage factors. The shrinkage factor in the parametric version, that's smooth because it's lambda. Whereas in the semiparametric version, that's basically zigzag. But you see the monotone structure. And it's interesting. Sometimes the for some cases, and the parametric version and semiparametric differs actually quite significantly. In other words, the semiparametric it doesn't go through the smooth curve. Actually, the general motions and the smooth curve they are actually separate from each other. So that's basically some indication of why the semiparametric behave better than the parametric. The parametric forces you to go some smooth way, where this one goes in arbitrary way, as long as it's monotonic. We do have some plots of that in the paper.
Just a quick question. So it seems to me that the parametric URE, for example, this quantity is quite close to the semi-parametric. Is this because maybe you did this arc sine transformation?
Not necessarily. Not necessarily. The parametrics will depend on how you view it. Sometimes, some cases they're close, but some cases are actually quite different. So this one is 0.63, and the corresponding.
Parametric URE, semi-parametric URE.
Yes, I'm comparing parametric. For example, toward shrinkage to weighted. You also talk about shrinkage toward weighted least square, ordinary least square, and sometimes it could be quite different. This 0.63, the corresponding version is 0.5. That could be quite different. I don't think I can conclude they are very similar to each other.
The last of
Yes, the last result are relatively close. Yes, but I don't have any further comment. I cannot give you an intuition why it is.
So let's speak.
Thank you.